Welcome to Part C of Unit 1 for our course on statistics. And where we left off last, I was talking about a standard deviation, and I was talking about how a standard deviation can be used to measure things. And now I want to look at one way that we can use a standard deviation to measure things. And I want to address that question that I raised a while ago when we were talking about all the questions we could address if Moniz had quantified his observations in his studies of lobotomies. And the very first question I raised is a question of, are scores high or low? That is, if you assess people and get their scores on a variable, and you get their scores on something, how do you decide if that score is a high score or a low score? And we can use the standard deviation to address this question to help us understand whether scores are high or low. So let's see how we can do that. So determining whether a score is a high score or a low score can be a very tricky and challenging thing to do. But it's something that we need to do. Anytime we conduct any kind of assessment, we need to address the question, if I get an assessment and get someone's score on something, I need to be able to determine, is that score a high score or a low score? And there are many, many places in life where we conduct assessments. If you're going into any kind of applied psychology, such as clinical psychology or school psychology, or industrial organizational psychology, these are all areas of psychology that make heavy use of assessment. So in clinical psychology, we assess clients cognitive functioning or achievement. We might assess clients for learning disabilities. We might assess a client's personality. We might assess a client's symptoms, maybe levels of depression symptoms or anxiety symptoms. So there are many things that a clinical psychologist needs to assess. Or if someone's in school psychology, a school psychologist would need to assess children's, say, academic achievement and assess their cognitive functioning, and maybe assess children's behavior problems. An industrial organizational psychologist would assess maybe employees at a company, or maybe applicants to a job and try to figure out which applicants are the ones that should be hired for the position. So there's many things that involve assessment. And of course, in education, throughout your experience as a student, you've taken many, many assessments, tests, and quizzes in class. Every time you take some kind of test, that's an assessment. And every time you have an assessment, we need to address the question, well, is this a high score or a low score? And it's something I think we often take for granted, but if we take a moment to think about it, that's actually a really challenging thing to do. Who's to say that score was a high score or a low score? How do we decide what we call high or low? And there's two things that make this especially challenging, especially in areas of psychology and neuroscience. One thing is that the scores we're looking at are going to be measured with arbitrary units. That is, there's not some universal defined unit. Say, for example, if I want to measure pain, there's no official pain units that I can measure pain in. So if I want to measure pain, I might have a scale that goes from, say, 1 to 10, but I could have just as easily made it a scale that goes from 1 to 100 or 1 to 3. The units that I use to measure pain are arbitrary. There's no universal standard for the units I should use to measure pain. And the same is true for anything else I would want to measure. For example, if I want to measure levels of depression, or if I want to measure cognitive skills, or someone's memory, or if I want to measure achievement, or if I want to measure personality, or depression, or self-esteem, those are all things that are measured in arbitrary units. And because these are measured in arbitrary units, it makes it difficult to figure out what's a high score or a low score. Now, another thing that can make it tricky to figure out what's high and low is simply the fact that the words high and low are relative terms. I can't call a score high without saying, well, high compared to what? And I can't call a score low if I say low compared to what? It simply doesn't make logical sense to call something high or low without comparing it to something. So the fact that we measure things in arbitrary units and the fact that high and low are relative terms are part of the things that make it tricky to figure out, well, how do we decide what a high score and a low score is? So let's take an example and see how we can use the standard deviation to solve that problem for us and help us decide what is a high score and what's a low score. So I went back to a few classes a few semesters ago, or actually it was a few years ago, and I took the final exam that the students in my statistics course took. And I got all the scores for the students on that final exam. And I don't usually grade things on a percentage, but for this class, for this example, I did. And I took all their scores and I graded and I looked at what their score was as a percent out of 100. So scores could range from 0% of the items correct to 100% correct. And then I just randomly pulled one student out of that group. So I had a group of students, they all took that final exam, and I have scores ranging from 0 to 100. And I randomly pulled one student out from that group, and this student had a score of 60 on that final exam. Now, if we're thinking in terms of, oftentimes courses are graded so that we say a 90% is an A, an 80% is a B, and a 70% is a C, and which is just an arbitrary way of grading things. I don't often use that. But if we did it that way, we'd say, well, a score of 60, that would be more like a D, right between maybe a D and an F. So we'd say, well, that looks like kind of a low score. That looks pretty bad based on that grading scale. But that doesn't tell us if it's a high score or a low score. Because if it turned out that everyone else in the class scored way down here, was down like in the 20s and 30s and 40s, well, then a 60 would actually be a pretty high score relative to everyone else. And even if I graded that and say, well, it's a 60, I count that as a D, well, that could be I could give it a D, but it still would be higher than everyone else if that person was higher than everyone else. Or in contrast, maybe, for example, maybe I got a student that got a 90 on the test, but if everyone else on the test got 100, that would actually be a low score. So just knowing that it's a 60 really doesn't tell us how bad that score is, or at least it certainly doesn't tell us whether it's a high score or a low score. So if I want to know, is this student got a score of 60 on my final exam, 60 out of 100, and I want to know, is that score of 60, is that a high score or is that a low score? So let's see how we can do that. So in trying to figure out if a score of 60 is a high score or a low score, it would really help to see what all the other scores were for all the other students in this course. And so what I have here is a histogram showing all the scores for all the students in the course. So we see here, here's one, and we had one student had a score somewhere between 15 and 20. One student had a score somewhere between 30 and 35. This is a 4 right here, so we had 4 students got between a 35 and a 40, and this would be a 3 right here, so we had 3 students between a 40 and a 45, and so forth. So with this histogram, we can see the shape of the distribution of the scores, which is something we'll be doing quite a bit in this class. We'll be looking at the shapes of distributions of scores in many places. So this histogram shows us the shape of the distribution of scores in this class. And we can see that the person who got a 60, that is kind of lower. The average score is somewhere probably right about there. So this person looks like that person is a little bit lower than average, but there's certainly several people that got a lot worse than 60. So that's really not a terrible score. It's a little lower than average, but it's not a terrible score. So when we see the shape of the distribution, when we see the other scores for all the other students in the class, it helps us give us a little bit of perspective about exactly how high or low of a score did this person right there get. A score of 60, exactly how high or low is that? Well, it looks like it's a little bit below average, but it's not a terrible score when we see the rest of the distribution. So one thing I could do that would help me determine whether a score is a high score or a low score is I could calculate a percentile for that score. I could calculate percentiles. And if I know the shape of my distribution, that is, I know how many people scored at each level along that scale, if I know what my distribution is, then I would be able to calculate percentiles. And percentiles just tell me what percent of people scored lower than a given score. So here's a score of 60. In this particular class, 23% of the students scored lower than 60. So a score of 60 is at the 23rd percentile. Or for example, here's a score of 40. In this class, 8% of the students scored lower than 40. So a score of 40 is at the 8th percentile. So we could convert scores to percentiles, and that would help us understand whether these scores are high scores or low scores. Notably, if I'm converting scores to percentiles, that's the same thing as talking about probabilities. These are two ways of talking about the same thing. I could calculate percentiles or look at probabilities. And what I mean by that is, for example, I could say, here's a score of 60. What's the probability that I randomly take one person from the sample and that person has a score lower than 60? The probability of randomly drawing one person from the sample and having that person score lower than 60 is 23%. So a score of 60s at the 23rd percentile, and if I randomly draw one person from the sample, there's a 23% probability the score will be lower than 60. Or here's a score of 90 up here. What's the probability that we randomly draw one person from the sample and their score is lower than 90? Well, it's 87%. So a score of 90 is at the 87th percentile, and the probability of randomly drawing one person from the sample with a score lower than 90 is 87%. So we can talk about percentiles and probabilities are two ways of talking about the same thing. And I point that out here because we're going to be talking about these types of probabilities throughout this class. We're going to have other situations where we'll have distributions of things, and I'll say here's a shape of a distribution, and given the shape of this distribution, we might take different points on it. So here's a point right here, and I want to know what's the probability of randomly sampling something from this distribution and getting a score lower than this point, or the probability of randomly sampling something from this distribution and getting a score higher than this point. And so we will be talking about probabilities in this way throughout this course. So one way we could determine whether scores are high or low is to simply calculate the percentile for each case in our sample. And one advantage of calculating a percentile is the fact that as far as statistical things go, percentiles are relatively easy to understand. There's many people, at least to some extent, understand what a percentile is. If I say you scored at the 70th percentile, many people would understand in general what that means. However, percentiles also have one big drawback. And this drawback is something that's, for this reason, we're actually not going to use percentiles very much in this class. And if you look at the screen, you might be able to figure out what this big problem is with percentiles. So at the bottom here, I have the top row of numbers. I call these would be the raw scores, the actual scores that people got on the test. And then the second row of numbers, these are the percentile scores, and shows what. So, and we see that, for example, a score of 20 corresponds to a percentile of 1, a score of 70 corresponds to a percentile of 40, and so forth. So these are the percentile scores in that bottom row. And if you look at these percentile scores, do you notice any problems with it? So what you might notice is these scores aren't very evenly distributed. If you are, say you get a score of 20, and you're at the first percentile, and you want to go up, say 10 percentile points. How far do you have to move up the scale to go up 10 percentile points? So from 1, so by 8, there's 15, so probably somewhere right about here might be the 10th percentile. You have to go about that far to go up 10 percentile points. So on the other hand, what if you have a score of 40 and you want to go up 10 percentile points? Let's see, well, there's 60, so it's halfway in between. So to go up, if you're at 40, you want to go up 10 percentile points, you just have to go just a smidgen. You just have to go just a short ways. Another way to think about this is that if you have a sample of 100 people, if you want to go up 10 percentile points, you need to pass 10 people. So how far do you have to travel to pass 10 people? Well, if you're way down here in a tail where there's not very many people down here, you have to travel quite a ways. You have to go a big distance to pass 10 people. On the other hand, if your score is right in the middle where there's a lot of congestion, this is where everybody is, you don't have to go very far to pass 10 people. And we can see that in our scale of percentile units, how it's not evenly distributed here. Going from a 1 to a 10 is not the same distance as going, say, from a 40 to a 50. One of these is a huge jump and another is a very small jump. So percentile units are distorted units. They're not evenly spaced units. They're units that if you're at the tails of a distribution, they're really, really spread out. And if you're at the midpoint of a distribution, they're all scrunched together. And for this reason, I often don't like to use percentiles. But if I'm trying to explain to someone where their score falls and they understand percentiles, it might be a useful thing to use. But for this class, given that percentiles distort the shape of the distribution, we're not going to use percentiles that much. So what are we going to do? If percentiles have this problem, what can we do? What type of score can we give that will tell us whether it's a high score or a low score that doesn't have this problem that percentiles have of distorting the distribution? Well, to address this issue and to develop a way for describing whether scores are high or low, we're going to take into account the mean and the standard deviation of our distribution. We're going to use the mean and the standard deviation as a method for describing whether scores are high or low. And at this point, we've been talking about the mean and the standard deviation, and you should have a good conceptual understanding of what the mean and the standard deviation are. And if you understand what a mean is and what a standard deviation is, you should be able to look at a histogram like this. You should be able to look at the shape of a distribution and give a good rough approximation of what you think the mean is and what you think the standard deviation is. So if you look at this distribution, why don't you do that right now? Take a look at the distribution here of these scores that I have of students that took the final exam for one of my statistics courses. And just by looking at this histogram, what would you guess? What do you think the mean is of this distribution? And we're looking at these raw scores down here. So, this person got a score of 60. That person looks like that person's below the mean. What would you guess the mean is for this distribution? And then, if you understand what a standard deviation is, you should be able to guess what do you think the standard deviation is for this distribution. Why don't you take a moment, maybe even pause the video if you need to, and guess what you think the mean is and what you think the standard deviation is, and then I'll show you what these values are on the next slide. So for this distribution of test scores, the mean is 72 and the standard deviation is 17. And on this picture here, I've drawn a red line, a vertical red line going up and down right at exactly the sample mean. So here's our, if you look at our number line down at the bottom here, score is 72. I'll draw a little triangle right here at 72, and you should be able to see that that's kind of a balancing point. It's a mid-balancing point of this distribution is the sample mean. And by looking at this distribution, you should have been able to guess that the mean is, well, about 72, or maybe you guess 70, or maybe 74, or somewhere in that ballpark. If you guess the mean was way out here, say at 95, well, that couldn't possibly be the balancing point. Or if you guessed the mean was way down here at 40, no, that couldn't possibly be the balancing point. So you should be able to look at a distribution like this and guess approximately where the mean is. It's that mid-balancing point for this distribution. In this sample, it's at exactly 72. And the standard deviation of this sample is 17. That is, if we use that formula for the standard deviation I was just talking about and use this data set, we would calculate that the standard deviation is 17, meaning that on average, people deviate 17 units from the sample mean. Or said differently, if we use the mean to predict each person's score, on average, the amount of mistake that we make will be 17 units. And I've drawn these blue arrows up at the top to represent the standard deviation. Each of these blue arrows is a line segment that's exactly 17 units long. The standard deviation is 17. This is how far people typically deviate from the mean. So the blue arrow shows you that on average, people deviate from the mean that much. So here I'm circling that blue arrow, and that blue arrow, that segment says that's on average how much people are deviating from the mean. And so you should be able to look at the sample and say, well, how far on average are people deviating? For example, if I drew an arrow way like this, here make a great big arrow to say, on average are people deviating, and this would be, whoops, I'm going way off on my line there. So this is like 70, maybe this is 60 or 70 points from the mean. Well, that's a huge deviation. People aren't deviating, no one's actually deviating that much. So that couldn't possibly be the standard deviation. Or what if I drew a line segment that would say only 5 units long? I'll go up at the top here and I'm going to draw a little arrow that say only 5 units long. Well, people are deviating on average a lot more than that. So you should be able to look at it and say, here, if you're at 60, you're deviating this much from the mean. And if you're at 40, you're deviating that much from the mean. If you're at 80, you're deviating that much from the mean. And if you're at 100, you're deviating that much from the mean. And 90 is this. So if you draw how far is each person deviating from the mean, and on average, what's the average size of these line segments? On average, how far are people deviating from the mean? How long are these line segments? And the average line segment that I'm drawing here would be 17 units wide. So going from the mean plus 17 units, here's my line segment on my right-hand side, my blue, and then on the left-hand side I have another line segment that's 17 units long, and each of those blue line segments is 17 units wide, because the standard deviation is 17 units, and that's showing you how far on average people deviate from the mean. So now let's take this information. I have this picture here where I've drawn where the mean is, I've drawn my standard deviation unit, and now let's use this to determine whether scores are high or low. So in the song about the standard deviation, the lyrics talked about how the standard deviation can be used to measure things. And that's exactly what we're going to do here. What I have here is the same histogram we've been looking at, the same distribution of test scores that we've been looking at, and I've marked off this distribution in standard deviation units. So we saw that our standard deviation was 17, and I drew these blue double-headed arrows that were exactly one standard deviation in length. The standard deviation is 17 units using our raw score units towards the bottom of our scale, the original scoring units that I used for my scale. And so if I use this number line towards the bottom here, we can draw a blue line segment that's exactly 17 units in length. And then I could say this line segment is equal to one standard deviation. That's one standard deviation unit. And then I can use these blue line segments to mark off the rest of this distribution. So if we go from the mean, I'm going to look at the top here. I've got this number line at the top, and I put a 0 right at the mean. And if I go one standard deviation unit below the mean, from the mean to one standard deviation below, I'm going to call that -1. And if I go one more standard deviation unit down below here, and it's just if I just took this blue line segment, I just marked it off in equal segments, equal standard deviation units. So here I have a -2 on my number line at the top. That is 2 standard deviations below the mean. And then at the top I have a -3, and that's 3 standard deviation units below the mean. Or towards the right, I have at the top I have a +1, which is 1 standard deviation unit above the mean, and then I have a 2, which would be 2 standard deviations above the mean. So I've just taken my standard deviation unit, this blue line segment, and I've used that to mark off my distribution in standard deviation units, and I've used the mean as a midpoint, and I called that 0, and I'm looking at how far scores deviate above or below the mean in standard deviation units. So using this standard deviation scale, we can say something more precisely about this person who got a score of 60 on the exam, where that green arrow is. So if you got a score of 60, I'll just draw a vertical line going up and down here, go way up to our top. If we look at our top scale with a 0, it's kind of between the 0 and the -1 there. And actually it's a score of 60, it turns out, is exactly 0.71 standard deviations below the mean. Or if I round that a bit, I could say it's about 7/10 of a standard deviation below the mean. So that's one way of describing this score of 60. A score of 60 is 7/10 of a standard deviation below the mean. So this process that I've been describing here is something that we call calculating z-scores for people. So a z-score is what we get when we go through this process where we first identify where the mean is, and we call the mean 0, and then we mark off our distribution in standard deviation units, and then I give people scores to indicate how many standard deviation units that person scored above or below the mean. That process is called calculating a z-score for a person. And so if you were someone that scored, say, 1/2 of a standard deviation below the mean, say right here, and that would be 1/2 of a standard deviation below the mean, your z-score would be -0.5. If you were 1/2 of a standard deviation above the mean, you would be +0.5. A z-score of 1 means you're exactly 1 standard deviation above the mean, or a z-score of -2 means you're 2 standard deviations below the mean. So that's a process where we call the mean 0, we mark off our distribution in standard deviation units, and then we give people scores to indicate how many standard deviation units each person scored above or below the mean, and that score is called a z-score. And for example, we looked at this person that got a score of 60 on that final exam, and we saw that that score was about 7/10 of a standard deviation below the mean. So that means that person's z-score would be equal to -0.7. Their z-score would be -0.7 because they were 7/10 of a standard deviation below the mean. Now, we could do this for every single person in the sample. We could go to every single person in the sample. We convert all their scores to z-scores. And actually, that's something we will sometimes want to do in this class. Sometimes there'll be situations where we'll have scores on a variable, and we'll want to convert all these scores into z-scores. And if we do that, it's essentially taking this distribution of scores, and we have the distribution towards the original raw scores at the bottom, 0, 10, 20, 30, 40, 56, that was the original raw scores, and we're simply going to convert it to this new scale at the top, and this new scale, I'm going to call that the z-score scale. So the numbers at the top is reflecting z-scores, that very top row of numbers, that's showing you z-scores, where this towards the bottom, that row down here, was showing us the raw scores. So if we could take everyone's score and convert it to a new scaling system, where 0 means you're right at the mean, and a -1 means you're 1 standard deviation below the mean, and a +1 means you're 1 standard deviation above the mean. So we could simply take the original scores and convert them to this new scaling system, is to convert it to z-scores. And if I did that, I would always end up with a new scaling system that always has a mean of 0 and a standard deviation of 1. So we could say it this way. We could say z-scores are the scores you get when you calculate the mean and call the mean 0, and then you mark off your distribution in standard deviation units, and then you give people scores to indicate how many standard deviations they scored above or below the mean. That's one way of defining what a z-score is. Or a simpler way to say what a z-score is to say it's if I give you a score on a scale that has a mean of 0 and a standard deviation of 1. That's also another way to define a z-score. Because note, that's what's happened here. Because in this top row of numbers, note I set the mean, right? I just said whatever the mean is, that's going to call that 0. So I created a scale by definition that will have a mean of 0. And because I marked off the scale in standard deviation units, because I used the standard deviation unit as my unit for the scale, that means that 1 unit will be equal to 1 standard deviation, which means this new z-score scale will always have a standard deviation of 1. So we can say a z-score is if I use a scaling system that has a mean of 0 and a standard deviation of 1, that's what a z-score is. And if I take people's raw scores and convert them to a new scaling system that has a mean of 0 and a standard deviation of 1, I can say I have transformed their raw scores into z-scores. So a z-score is a very effective and useful method for answering that question about whether a score is high or low. A z-score tells us whether a score is high or low by telling us how many standard deviation units a person scored above or below a mean. And that's useful because a standard deviation will always mean the same thing. A standard deviation always means the average distance that people deviate from the mean. So regardless of what our original scale was, we might have a scale that goes from 0 to 10 or 0 to 100, whatever our scale is, a standard deviation unit always means the same thing. It's the average distance that people deviate from the mean. And because a standard deviation always means the same thing, a z-score scale will always have the same meaning. It will always tell us how far people scored above or below a mean in standard deviation units. So it's very useful in that respect. Now, one thing that makes z-scores maybe not quite so practical in some settings, especially For example, if you're a clinical psychologist or a school psychologist and you're doing assessments on clients or children, and maybe you need to give feedback to clients, or you need to have discussions with other professionals about your assessment results, there's a couple things about z-scores that make them a little bit impractical to use in those settings. One thing is that z-scores will always be very small values. You'll be dealing with a lot of decimal points when you're dealing with the z-scores. You might get a score of 0.38 or negative 0.26 or something like that. So z-scores are small values, and you have to be dealing with a lot of decimal places to talk about z-scores, and that's not always practical to do. And the other thing about a z-score is that z-scores can be negative or positive depending on whether you're above or below the mean. And sometimes if you're giving someone feedback and say, well, your score on this cognitive achievement test is a negative 0.3, that person might be kind of thrown off. What, I got a negative cognitive achievement score? That's kind of scary. How did that happen? And so z-scores can be positive or negative, whether or not, depending on whether their score is above or below the mean. But sometimes it would be nice to have scores that or at least don't usually take on negative values. And we can fix this by simply transforming the z-score scale into some other type of standardized scale. So, and one very common scale to use is something called a t-score scale. And so where a z-score is a scale that has a mean of 0 and a standard deviation of 1, if we wanted to, we could just change the z-score scale into a t-score scale that will have a mean of 50 and a standard deviation of 10. And note, I've done this at the very top here. So at the very top of the slide, you see one scale. The first one is the z-score scale, and the one right below it is a t-score scale. So where the z-score has a mean of 0, and I put the 0 right there at the middle of my z-score scale, I'm just going to change that to a 50 for my t-score scale. And when I go up one standard deviation for a z-score, a 1 is one standard deviation above the mean. For the t-score, I'm going to go up, I'm going to make each standard deviation worth 10 units. So I'm going to go up from a 50 to a 60. And for the t-score, one standard deviation below the mean will be a 40. So at the top of the slide here, we have two types of distributions, two types of scales. The first scale, at the very, very top, is the z-score scale. And then immediately below that is the t-score scale. And a t-score is something you might want to use in an applied setting where you don't want to deal with tiny little z-score values, and you don't want values taking on negative scores. And we can interpret it the same way. So with a t-score, we know that a 50 is right at the mean and 40 is one standard deviation below the mean. So for example, if someone was one standard deviation below the mean, their z-score would be -1. So if someone gets a z-score of -1, we know that's one standard deviation below the mean. Or if we're using this t-score system with a mean of 50 and a standard deviation of 10, a score of 40 would be one standard deviation below the mean. And if someone, say, let's look at two standard deviations below the mean. So if you're two standard deviations below the means, your z-score would be a -2 and your t-score would be a 30. Or if you're one standard deviation above the mean, your z-score would be 1 and your t-score would be 60. So these are two different scoring systems based on the mean and the standard deviation. And because these scoring systems are scored in standard deviation units, and because standard deviation units will always mean the same thing, these scales will always have the same consistent meaning. So you can, if you get someone's z-score and their z-score is, say, 1.5, you know that person's 1.5 standard deviations above the mean. And if you get someone's t-score and their t-score is, say, 65, you know that person is 1.5 standard deviations above the mean. So we can use both z-scores and t-scores to interpret people's scores. So to review everything we've been talking about, let's go back and look at that person that got a score of 60 on the final exam. I'll draw a line right here going up and down right at about 60 there. And we can see that a person that got a score of 60, if we look at the scale towards the bottom, which is our raw score scale, that score was a 60 right there. So their raw score was a 60. And then if we go at the top and look at our z-score scale, if we say how many standard deviation units did this person score above or below the mean, this person scored about 7/10 of a standard deviation below the mean, and precisely their z-score was a -0.71. So using this top z-score scale this point right here, I'm drawing a little dot there, right about there, that's a z-score of negative 0.71 on that z-score scale. Or if I look right below it on this t-score scale right below it, that's a t-score of 42.9. That's exactly where that t-score falls. And both a t-score of 42.9 and a z-score of negative 0.71, if we round it to a z-score of negative 0.7 or a t-score of 43, in both cases that tells you that person's score is about 7/10 of a standard deviation below the mean. So we can look at that person's score in terms of a raw score using the raw score scale at the bottom. We can look at that person's score in terms of a z-score at the very, very top. Or right below that, we can look at that person's score in terms of a t-score. Are three different ways of describing that person's score. So now the next question is, well, how would you calculate a z-score and how would you calculate a t-score? Are there formulas that we can use that are simple and easy to use to plug in to calculate a z-score and a t-score? And indeed, there are formulas. And if you think about it, you might be able to figure out what those formulas are. I'll show you what those formulas are on the next screen. But maybe, if you can, maybe pause the video here and see if you could even guess what these formulas are going to be. So what formula would we use to calculate a z-score, and what would we use to calculate a t-score? And here are the formulas we can use to calculate a z-score and a t-score. At the top I have the formula for a z-score. So to calculate a z-score for a person in a sample, I take that person's score on x, the score on x for individual I, and I subtract from it the sample mean, x bar. And then once I have that, I divide that by the standard deviation, and that will give me a z-score for that person. That will tell me how many standard deviation units that person scored above or below the mean. Now, note that this formula for a z-score has two components to it, or two parts to it. The first part is we take a person's score on x and we subtract the mean from it. And the second component is we divide that by the standard deviation. And let's consider these two components in a context where maybe I have a sample of people and they all have scores on variable x, and I want to convert everybody's score into a z-score. Everybody has a score on x, and I want to turn all those scores into z-scores so that every single person in my sample will have their z-score on variable x. That's actually something we will often want to do in this class. There'll be many situations where I'll say, here's a sample of people, and before we do anything, let's convert everybody's scores into z-scores. So if we did that, our first step is we take everybody's score on x, and for every person in our sample, we'd subtract the mean from that person's score on x. Now note that this is actually the exact same thing we did as the first step in calculating a standard deviation. The first step of calculating a standard deviation was to subtract the mean from everybody's score. And recall at that point, I call those error scores or deviation scores. These were told us how far each person deviated from the mean, or the amount of error that we made when we used the mean to predict that person's scores. And we're doing the same thing here. We're subtracting the mean from everybody's score. And recall that when I talked about those deviation scores, I mentioned that the mean, the average of those deviation scores will always have an average of 0. Another way of saying the same thing is that if we calculate these deviation scores will always be centered around 0. And for that reason, if I have a sample of people and I create these deviation scores, that is, I subtract the mean from everybody's score, I will say I have centered scores. If I tell you, I want you to center the scores, what that means is I want you to subtract the mean from everybody's score. And when you do that, you will have a new set of scores, and this new set of scores will, by definition, have a mean of 0. So if you subtract the mean from everybody's score, that will give you a new set of scores, and that new set of scores will always have a mean of 0. And for that reason, I call that a centered score. It means it's centered around 0. Now, recall that this is one of the key properties of a z-score. I mentioned that a z-score is a score that has a mean of 0 and a standard deviation of 1. So to get a scale that has a mean of 0, we simply center the scores. that first part, this process of centering scores, is the part of the formula that gives it that property, so we get a score that has a mean of 0. And the next thing we want is we want to have a scale that has a standard deviation of 1. And so to get that part, to make it so that we have a scale that has a standard deviation of 1, we simply take our centered score and divide it by the standard deviation. And if we did that for every single person in the sample, their new scores would be z-scores, and these z-scores by definition at that point would be scores that have a mean of 0 and a standard deviation of 1. And then at this point, if I wanted to create a t-score, it's easiest to first calculate the z-score, and then if I wanted to transform that into a t-score, I simply take my z-score, multiply it by 10 to give me a standard deviation of 10, and then add to that 50 to give me a new scale that has a mean of 50. So if I take my z, multiply it by 10, that will give me a new scale with a standard deviation of 10, and then if I add to that 50, that will give me a scale that has a mean of 50. So we can say the t-score is equal to 10 times the z-score plus 50. Now note that we could actually transform this into a scale that has any mean we wanted it to have and any standard deviation we wanted. So for example, I could say I want a scale that has a mean of 100 and a standard deviation of 15. Actually, there are some types of cognitive tests that use that type of scaling system. And if I wanted to use that type of scaling system, I could transform this into a scale that has a mean of 100 and a standard deviation of 15 by simply taking my z-score times 15 and then add to that 100, and I would get a new scale that has a mean of 100, standard deviation of 15. So the basic formula simply goes like this. I take my z-score and multiply it by whatever value I want to be the standard deviation for my new scale. And then I add to that the value that is whatever the mean is that I want to be for my new scale. And I want to have a new scale that has the desired standard deviation and the desired mean. And all of these scales, I'm going to call these standardized scales. So a standardized score is a score that's based on z-scores that has based on standard deviation units. So if I create a z-score, because it's based on standard deviation units, I'm going to call that a standardized score, because standard deviation units always have the same meaning. And so if I base my scaling units on standard deviations, it's a standardized score because standard deviations always have the same meaning. And if I transform my z-score into a t-score or into any other type of score that has a set mean and standard deviation, I'm going to call that a standardized score. So a z-score and a t-score, these are both examples of standardized scores. And any system where I set my scale to have a specific mean and a specific standard deviation, I'm going to call that a standardized score. So we've been looking at this distribution of scores. This is a distribution of test scores from students taking a final exam in one of my courses. And the shape of this distribution is somewhat irregular. For one thing, scores are kind of skewed, where we have quite a few scores clustered together towards the upper end, and scores are more spread out towards the lower end. And the shape of this distribution kind of goes here, it kind of steps up there, then goes over like a stair step there, and then goes way up here, and then goes up and down a bit. So I would say the shape of this distribution is somewhat irregular. But that's not always the case. In fact, very often we might collect data from people, we might assess a group of people, and then look at their scores and look at the distribution of those scores. And it's very, very common to discover that the shape of that distribution takes on a more standardized or more systematic type of shape. For example, here is a distribution of scores that takes on much more of a well-formed shape here. This distribution of scores comes pretty close to following this black line, this curve that I've drawn on here, this bell-shaped symmetrical curve that I've drawn there. This distribution of scores comes pretty close to fitting that shape of that black line. And that black line that I've drawn, that bell-shaped symmetrical curve that I've drawn here, is actually a very specific type of curve. That curve is actually defined by a mathematical formula. And it's a curve that we call the normal curve, or the normal distribution. So the normal distribution is a curve that's defined by a mathematical formula. And it's very, very common to collect data from people or to collect data from cases, and then to look at the scores on a variable and to discover that the distribution of the scores comes really, really close to fitting this normal distribution. Now, chances are the distribution of scores is never going to perfectly fit a normal distribution, but oftentimes it will come really, really close. And if it comes really, really close, then we can say it's close enough to use that normal distribution to determine probabilities. So recall what I was saying before. If you know the shape of a distribution, then you can use that shape of the distribution to determine probabilities. If you know what the distribution looks like, then you can say, for example, what's the probability of someone scoring lower than this point? Or what's the probability of someone scoring higher than this point? So if we know the shape of a distribution, we can use that shape to determine probabilities. And if you have a distribution of scores on a variable that comes really, really close to a normal distribution, then we can use this normal distribution to determine probabilities of those scores. Now, one thing to keep in mind is that there's actually other shapes out there that are defined by mathematical formulas. There's other types of distributions that can be defined by mathematical formulas. And so the normal distribution isn't the only one, but it's going to be the most common one we will encounter. And it's the one I want to introduce to you right here. Also, we're going to be talking about, right now we're talking about distributions of scores from people in a sample. And we're looking at how these scores might come really close to fitting a normal distribution. We're going to be looking at other things in this course that actually will fit a normal distribution or actually will fit another type of mathematically defined distribution. And so I want to start off by looking at the general idea of how we can use distributions to determine probabilities. We can introduce this idea by talking about if I have a distribution of scores from people, and if that distribution comes close enough to a normal distribution, how can we use the normal distribution to determine probabilities? And then that will set us up for future discussions about if we have distributions of other things that might fit, maybe perfectly fit a normal distribution, or maybe perfectly fit other types of distributions, how we can use those distributions to determine probabilities of other things. So we're going to talk about using the normal curve to determine probabilities of scores of individual people, and that's going to set us up for bigger and better things yet to come. And here is another picture of what the normal distribution looks like, this symmetrical bell-shaped curve right there. And in the upper right-hand corner of the screen, I have the formula that's used to create the normal distribution. Now, we're not going to do a whole lot with this formula in this class, but I do want you to know that this formula is used to create this normal distribution. If we plugged in different values for x, it would return values on y, and if we plotted those values, we would get this shape right here, this symmetrical bell-shaped curve that we're looking at, the normal distribution. So the important thing to know is that the normal distribution is defined by a mathematical formula. And because it's defined by a mathematical formula, it will always take on exactly the same shape. It's a precise shape. It will always be the same shape because it's defined by a formula. And if it always takes on the same shape, then it means that standard deviation units will always fall at exactly the same place along this distribution. I've marked the standard deviation units in the figure below here. So the numbers at the bottom of this bell-shaped curve are showing you where the standard deviation units would fall. So I put a 0. This will be right at the mean. And here's a 1. This is the 1 standard deviation above the mean will always fall right here. That is, if I collected data from a group of people and got their scores on a variable, and if their scores fit the normal distribution, if the scores had a distribution that was pretty close to the normal distribution or fit exactly the normal distribution, if the scores fit this shape, then 1 standard deviation above the mean would always be exactly right here, and 2 standard deviations above the mean would always be exactly right here, and 1 standard deviation below the mean would exactly be right here, and so forth. And of course, what I've drawn along the bottom here, you should recognize, well, these are z-scores. So in other words, if I have data and the data fit the normal distribution, if I have data on a variable and the shape of the distribution of those scores fits a normal distribution, then I know exactly where the z-scores are. The z-scores will be right here. So these are where the z-scores will be for a normal distribution. That is, that's where the standard deviation units will be. One standard deviation above the mean, a z-score of 1 is right there. Two standard deviations above the mean, that's a z-score of 2, will be right here. One standard deviation below the mean, that's a z-score of -1, will be right here. So if I have data that fit the normal distribution is defined by a mathematical formula. It will always have the same shape, and so the standard deviation units will always fall at exactly the same place within that normal distribution. So if the normal distribution is defined by a mathematical formula and will therefore always take on the same shape, and therefore z-scores will always fall at the exact same points along the normal distribution, it means that if we have a set of data, we have scores from a set of cases, and those scores fit a normal distribution, if I know the z-score for any one case, then I know the area under the curve above or below that case. And that's what I'm depicting here on the screen. So here we have the normal distribution, and I have the z-scores, and these will always fall at exactly these same points along the normal distribution. So here's a z-score of -1, here's a z-score of -2. So if I collect data from a sample of cases, and if the scores on this variable fit a normal distribution, if I find someone who has a z-score of -2, that's 2 standard deviations below the mean, and that will always fall right exactly here on this distribution. And in this case, it will always be true. Now I've actually rounded this just a little bit, but with rounding, it will always be true that 2% of the cases are below that point, and 98% are above that point. So if you're 2 standard deviations below the mean, and if we have scores that fit a normal distribution, it will always be true that 2% of the cases are below a z-score of -2, and 98% are higher than that point. And I've filled in some other scores here too. These are actually all with rounding, but it will be the percent of area under the curve between -1 and -2 will always be 14%. Or we can say it this way, that if you have a z-score of -1, 14% plus 2%, 16% will be below that point, and 84% will be above that point. Or we could do it over here. Here's a z-score of +1, 16% will be higher than a z-score of +1, and 84% will be below that point. And if we have scores that fit a normal distribution, this will always be true. And the percentages that I put on this page here would be good to have memorized, because we're going to be using a normal distribution throughout this course, and there's many points where it would be helpful to have a general sense of the areas under the curve. So to know that 2% of the cases will fall lower than a -2. 14% will fall between -2 and -1. Or over here on the positive side, 14% fall between +1 and +2. That is, 14% fall between 1, which is 1 standard deviation above the mean, and a 2, which is 2 standard deviations above the mean. And 34% will fall between a 0 and a 1. And so we can say things like, if you have a z-score of 1, then we would know that you are at the 84th percentile, because 84% of the cases are going to be lower than that, and 16% are going to be higher than that. That's if the scores fit a normal distribution, that would be true. And if you have a z-score of 2, then we know that you'd be at about the 98th percentile, with 98% of scores lower than that and 2% higher than that. And now if we want to be more precise than that, we can be more precise. We could actually figure out, for example, if you had a z-score of, maybe that's a z-score of 6, maybe a 0.67 or something like that, we could figure out what the probabilities are, what the percentage are. We could figure out what percent of cases are lower than a z-score of 0.67 and what percent are higher than that. But we'd usually use tables or calculators to do that. That gets a little more complex, but we can do that, and we will be doing that in places. But if we want to do something like what a z-score for 0.67, that's something I wouldn't memorize that. I'd look that up in a table or use a calculator to get that, and I'll show you how we can do that later on. But for right now, I want you to memorize these basic cutoffs to know things like if you have a z-score of 1, you're at the 84th percentile. A z-score of 2 would be at the 98th percentile, because this will become very handy in many situations as we go through this course. So to review, if I have a distribution of scores for a variable, and if that distribution fits a normal distribution, then we can use the normal distribution to determine things like percentiles and probabilities. So for example, if someone has a z-score of 2, that means there are 2 standard deviations above the mean. And if the data fit a normal distribution, then it will always take on exactly the same shape, and 2 standard deviations above the mean will always occur at the exact same spot along this distribution. And it will always be true that 98% of the scores are below that point, and 2% are higher than that point. And so we could determine that person's percentile. That person, if you have a z-score of 2, you will be at the 98th percentile if the data are normally distributed. We could also determine probabilities. Now, I'm most likely to ask you questions where I give you a high score and say, what's the probability of getting a score higher than this? Or where I give you a low score and say, what's the probability of getting a score lower than this? In other words, my questions are often likely to ask about probabilities going towards the tails. So I might say, here's a high score of a z-score of 2. What's the probability of someone scoring higher than that? And the answer would be 2%. Or we might say, here's a z-score of -2. What's the probability of someone getting a score lower than that? And that would also be 2%. Now, I could ask the question this way. What's the probability of getting a score more extreme than 2? So, for example, if I have a z-score of +2, if I say more extreme, what I mean is in either direction, further away from the mean in either direction. So a score more extreme than 2 is a score that's higher than +2 or lower than -2. So if we compare these two questions, the probability of, say, getting a score higher than 2 or more extreme. So if I have a z-score of 2, the probability of getting a score higher than 2 is 2%. The probability of getting a score more extreme than 2 is, I double that, 4%. 2% here and 2% in that tail. I just take the probability of getting a score higher than 2 and double it to get the probability of a score more extreme than 2. Because more extreme is asking about it going in either direction. So there's a 2% probability of getting a score higher than +2, a 2% probability of getting a score lower than -2. Put it together, I get 4% altogether. Now, in the next lecture add-on videos, we'll be looking at situations where we might look at more precise z-scores. Like I might say, here's a z-score of, say, 1.26. And I want you to give me the probability of getting a score, say, higher than a z-score of 1.26. And to do that, we need to look that up on a table or use a calculator. And the lecture add-on videos will show you how you can do that. But for right now, the thing to know is if you have these percentages memorized, you could look at these things up, or you could figure out these without even looking them up on a table, without using a calculator. If I say someone has a z-score of 1, you just automatically know, well, that person's at the 84th percentile. The probability of getting a score higher than that is 16%. And that is everything for Part C of Unit 1.